Real quickly, we're going to talk about a different kind of system. We're going to introduce a different kind of system. So this would be a linear quadratic system, where we've got one linear equation, and then we've got one equation that's got x squareds or y squareds, or in this case, both. So, yes, sir. I am recording. Thank you for checking. So first of all, let's just review a couple things about how we can solve this with technology. So we would just use Desmos, right? If we're looking for the solution to a system with two equations, we'll just graph it in Desmos. And the really nice thing about Desmos that makes this a lot easier is that I don't have to solve for y, right? I can just solve this. I can write these equations just the way they are. I don't have to solve for y. I don't have to do anything fancy like that. Now, what do you think this first one's going to look like? Where the x's and the y's are being squared. So I get x minus 4 quantity squared. It's going to look like a circle. Okay, so it is indeed a circle. There it is, right?
Wow.
And a line. Okay, I want to point something out, though. When you're looking for intersections on Desmos, sometimes the graphs are not very convenient. Sometimes, in this case, it's pretty obvious, but sometimes it's difficult to see where exactly the intersections are. And I'll pull up another example here in a second that'll make that a little clearer. But if I want to find the intersections, if I want to find any important points on a graph in Desmos, watch what happens when if I just click, I can drag a point around any function, or this isn't even a function, right? It violates the vertical line test. But any graph, I can drag a point around, and I can kind of see the coordinates change as I drag it. But those points don't stick. As soon as I click on any kind of a graph, though, notice that there's a bunch of light gray points that pop up. Okay, what do you think those are?
Intersections.
So important points, yeah. So intersections, like what's that one, for example?
Y-intercept.
Okay, so there's a y-intercept. If I click on those, they stay, right? I can see the coordinates. What's that one?
X-intercept.
X-intercept. There's another. Looks like there's a minimum, right? So that's the lowest point. There's a maximum, highest point. Now what are those? Intersections between the curves, right? So it gives me, it just gives me a handful of special kinds of points on a function, including intersections between graphs. And so it makes it pretty easy to find the intersections between graphs, right? So on this one, what were we looking for? We were looking for ordered pairs. Well, there they are, right? 9, 1, and 5, -3. Okay, I'll show you one other little example with this. I think it's that one. No, not that one. Oh, not that one either. Yeah, this one. Okay, look at this guy. So what if I'm trying to find the intersections of those two curves? Like I've got this, I'm solving an equation where I've got that expression right there equal to that expression right there. So I just graph each side of the equation. But in this case, look, it's difficult to find where the intersections are. The curves are so close together, right? I can make this really simple, though, if I just keep in mind that Desmos only gives me the important points, right? If I click on, like, the red graph, where are the intersections between the curves? Right there, right? It makes it really easy to find, because those couldn't be anything else. Those aren't intersects, y-intercept or x-intercepts. They're not the vertices, minima or maxima of a function. So they have to just be intersections between curves, right? Okay, so it's easy to find using Desmos. Stuff like this is really simple. I just graph them and I find the intersections. Okay, so what do you think is going to happen? I'm not going to do this whole system, but what do you think is going to happen with that top equation up there? If I graph that. Now just think about that for a second. So normally we'd have y equals x squared plus 6x plus 4 would be a normal thing, right? But this time we've sort of swapped the x's and the y's, haven't we? Right? So the y, or the x is the variable that's by itself, and the y is the variable that's being squared. Let's take a look and see.
Maybe. Yeah, because it's going to be end up getting square rooted if you move them all.
Uh-huh. Okay, so let's see what happens here. If I graph the function, actually it's not a function, the relation, y squared, we'll see why it's not a function in a second. And let's just click home, and sure enough, what do you see? Sideways, right? Okay, that shouldn't be that surprising. If I'm exchanging the x's and the y's, then now whereas the x-axis used to be the axis of the independent variable and the y-axis normally would be the axis of the dependent variable, it's going to be, we're switching it around, aren't we? And so if I were to do something like, what if I were to put this into vertex form? So what if I were to put this into the form x equals a times the quantity y minus h squared plus k, something like that. What do you think the meaning of the a and the h and the k would be here? And this isn't something crucial for the stuff we're going to talk about, but I just want you to think about this a little bit. Those were, if we switch the x's and the y's, that's pretty simple, right? A always meant vertical dilation factor, right? H always meant the x coordinate of the vertex, and k always meant the y coordinate. But now that I've swapped the x's and the y's, what do you suppose that a has become now? Yeah, became the horizontal dilation factor. So it's telling us how far have we stretched the function or compressed it from the y-axis horizontally, right? What do you think the h became? The what? The y coordinate of the vertex, and the k became the x coordinate of the vertex. Say it again. Yeah, it's still a vertex. Yeah, and you know what we deal with. It's a non-function, isn't it? Because it violates the vertical line test. Well, it's not a function of x. It's a function of y, right? But when we start talking about functions of y, it's no longer the vertical line test that applies. It becomes probably what? Okay, so functions of y would have to pass the horizontal line test, and so it would, right? So it's kind of cool that in math you can do stuff like that. And later on in the year, we'll come back and we'll revisit this topic when we talk about inverses. And we'll see that really this is where it leads us, is into this kind of a situation where we're going to swap x's and y's, and we can draw some interesting conclusions about relationships between functions and their inverses, the kinds of symmetries they have. But you see this, and I just want to kind of get you thinking along these lines, because in math a lot of times when we talk about symmetries, you're used to, when we talk about a symmetry, you're used to a graphical symmetry, right? Geometric symmetry. You talked about that a lot in geometry class. We've talked about it a little bit this year. We've got symmetries like reflective symmetry, over the y-axis, or rotational symmetries. But a lot of times you can even see symmetries just in the algebra, right? And you can kind of think of it that way. If I'm swapping the x's and the y's, then really those are just symbols, right? They're symbols that we attach, to certain axes, the x-axis and the y-axis. But there's nothing magical about the horizontal versus vertical, right? There shouldn't be any real preference geometrically for moving sideways or up and down. They're just directions. And so when I swap the x and the y variables like that, we really should expect that everything's going to behave essentially the same way, only the behavior is just going to be it's going to be altered in a way where the x's and the y's are just substituting one for the other. And so the behaviors are going to change accordingly, right? And as you start to think about math more and more, a lot of times you can make predictions about what the physical symmetry is going to be or the geometric symmetry just based on what you did with the variables, right? And so this is like just the opening little piece of a conversation we'll continue later. But there's some problems like this on the assignment, so I wanted you just to be aware. I mean, you don't really need to know much about them. You can still do the algebra the same way as before. But in the back of your mind, it's kind of nice to just have an idea, how are these functions a little bit different, right? Well, I got 2 minutes, so I don't think I'm even going to bother with the next step. But so I put up, the first assignment I put up over linear quadratic systems is graphical, so you don't need to know anything other than what I just showed you. There's 5 problems. You know, you'll have most of the period today. You can work on that if you want. And maybe we'll come back tomorrow and we'll look at, the next step is just going to be this. The next step is going to be, how do we solve these things algebraically? What if we've got a linear quadratic system where I've got a linear equation and a quadratic system? How can I find the intersections algebraically? And you're going to, when we talk about this, you'll know. I mean, intuitively, you'll probably know what to do, but I want to go through a couple examples. Right? And there's some little tricks you can do sometimes that make the algebra a little bit easier. So we'll go through that tomorrow. Call her quits for today. All right. Have